Good morning, fellow mathematicians. Eat further. Welcome back to another video. Today we are going to do a tier list. One that has been overdue for as long as humanity exists. Mathematical constant tier list. We are going to finally talk about it. We are going to sort the best mathematical constants today into 5 main ranks. SZ, small a, successor of capital A, capital C, and parentheses X, D. I hope you are going to enjoy the video. Now I dropped the paste. I'm so incompetent. And shall we start? Yes, we should. And we are going to begin with the mighty number 1. So you might ask yourself, what is special about the number 1? I mean, it's a number like any other. Am I right? No, you are not right. The number 1 is something really special. The number 1 is the start and probably in some number systems also the end. It's the alpha and the omega. It's the start for the theory of Mohammed Ababu. It's the multiplicative identity. If you take one apple, you only have an apple. If I bang your mom only once, I only banged your mom once. 1 times anything is just a thing in itself. And this is the beauty of number 1. But it doesn't end there. If you add 1 to something, then it's going to be 1 more than the something. 3 plus 1 is 4. It's the successor of 3. Or how I like to call it in my bachelor's thesis, suck of 3. And since it's so majestic, since it's a successor, it's going to get a B rank because it's the successor of nothing. 1 is the only number which is not a successor of any other number, at least if you define the Peano axioms starting at 1. It's outright beautiful, don't you agree? Next one, let's continue with the successor of 1, the number 2. What is special about the number 2, you might ask? Well, number 2 is the oddest of all prime numbers. And I don't speak in terms of parity. It's not an odd number, but it's really odd because it's the only even prime number. Isn't that fucking weird? I mean, it's rather weird. And this is why I think the number 2 is pretty cool. And also, the number 2 is, no, it's just a regular number. There is not much more to do. It's just a regular fucking number. And yeah, it's twice the number 1 and the successor of 1. So yeah, since there's really nothing special about the number 2, we are going to put it into the D rank. It just sucks. I mean, it's the only even prime, but that's basically all about it. But do you know what doesn't suck hard? The contents of today's sponsor, Brilliant, who are kind enough to sponsor yet another video here on this channel. You know, the greatest thing about Brilliant and their team is most definitely that they are cool with memes. I mean, you don't find sponsors like this everywhere. Not everyone is cool with doing meme stuff on an educational channel, especially if the platform in and of itself that you are trying to convince the viewer to buy into is also an educational platform. But for some reason, they're cool with it and I just love it. And speaking of education, Brilliant is one of the best sources that you can find online, if not the best source, at least in my opinion, to learn new things on a daily basis in all topics STEM, be it the mathematics that we did today, physics, computer sciences, chemistry. No matter what it is you're striving for to learn in the STEM field, Brilliant definitely got something up the sleeve for you. Now, just imagine you want to learn something about calculus. I know it's not really in the sense of this video, but calculus, there are a few constants that appear there. And maybe you don't know yet what a derivative is. Brilliant, and trust me with that, can help you learn what a derivative is. Visually as well as formally, but most importantly, visually at first. Derivatives are nothing other than tangents, okay? Tangents being put onto a curve. And visualizing this can be rather hard on a chalkboard, for example. But if you use a website like Brilliant, it's going to be an easy feat because, for example, take a parabola or whatever. And if you want to find the derivative, you're going to adjust a tangent line to it and you can swing it around. And with this idea in mind, you can even find out what the maximum and minimum of this function is going to be, namely where the slope of the tangent line is going to be 0 and the like. And they're doing this all the time. On their website, all over the place, you're going to find visuals that you can play around with varying parameters such that you can find out something about functions and the like. In the geometry section is one of my most favorite examples. You can play around with the angles to see that the interior sum of the angles are going to add up to 180 degrees, and just everywhere. The whole website is being backed up by graphics like this. And it's a lot of fun to play around with, and you're most definitely going to learn something new every day, just like I do. I'm an avid Brilliant user and I'm learning something new on a regular basis, even though I'm already a professional teacher, you could say. And if I can learn something new, you can do so too. And the best way to learn more about Brilliant is to experience it by yourself by using the link at the top of the description, brilliant.org/flammable-maths. With it, you are going to get free access to a big portion of Brilliant already, but more importantly, first 200 people to actually make use of the link get 20% of an annual premium subscription, which is a great deal considering how much content they already have available on the website and how much content they are adding on a regular basis. You are virtually never going to run out on content over there. So definitely make sure to check it out and support the channel this way. And now we are going to continue with the very important tier list that no one asked for. Let's go. Now, next, after the 2 comes the square root of 2. Why is the square root of 2 an important mathematical constant? I wouldn't really call it important, but it's most certainly the first irrational number you're going to deal with. I mean, square root of 1 is nothing special because it's just going to give you 1, but once you deal with square root of 2, it's going to throw everything apart that you know about rational numbers, at least from school. And the same thing happened to Pythagoras. This is why it's called Pythagoras constant in the mathematical community. This number fucked him in the arse pretty goddamn hard. And why? Because back in the days he thought, well, all the geometry worked with just natural numbers. You get natural numbered side lengths, for example 3 and 4, and the right triangle that is going to be formed by those two cathets is going to give you another natural numbered side length like 5. And then one of his students came and drew a unit side length here in a right angle with another unit side length. 1 squared plus 1 squared is going to give you 2. But if you then take the square root of that, okay, you're going to have a bad time. Pythagorean theorem. And I can just suppose that the student has been beheaded or something like that. But since square root of 2 fucked his whole view on the world in the arse in just a moment, most definitely gives it a higher tier. Let's put it into the S tier. No, into the A tier. Or it banged him in the ass. Let's give it an S tier, an SZ tier. Now next up, we are going to deal with the number pi. I mean, the number pi is really nothing special, it's just a successor of 2. But there are many myths surrounding it. Some people claim that its decimal representation, even though it's non-existent, it doesn't have any decimal point after the 3, is infinitely long. And it also does not repeat. That's what you call an irrational number. But also, some people claim, even though it's just a rational number, natural number at that, they claim that it's also not the solution to any polynomial with rational coefficients. That's what you call a transcendental number. I can only disagree, talking to engineers at least. But some people claim that it's such a number. And since so many people claim that it's not equal to 3, which I don't agree to, it's going to get an A tier. And because it's important sometimes, it sometimes appears in mathematics. But all the myths surrounding it in the engineering community just make it already a great number. Speaking of pi, there's a number that you probably guessed that this is going to come next. There's a number which is equal to pi. This number is called Euler's number. I mean, it's also just a successor of 3. And since it's equal to pi, it also should go into the same tier as pi. Namely, E is equal to pi. I should put in equal signs between those two. But yeah, nothing special there, okay? They are both equal, they just have different names. And it appears sometimes in mathematics, not often. It's not like it's the most natural constant out there. Just appears sometimes, it's an A, okay? We can all agree. Now next up, one way more important constant, the golden ratio phi. Now what is the golden ratio phi? Some people claim that the golden ratio is everywhere. If I take a shit and the shape that my body makes is in the golden spiral, in the golden relationship, people say that it's there. If you go over to Joe, it's going to be there. He's lying in his bed because his dog just now died and he's in a fetus position. Golden ratio, golden spiral there. The golden ratio is everywhere, our universe, everything. Let the sheep believe whatever they want. But since it's so annoying, and so many people talk about the golden ratio like it's everywhere and shit, it's just a ratio like any other, okay? There are many metallic ratios out there. It's going to go into the C tier just because it's so annoying in internet culture and also in pop culture. Next up, we have a constant that I don't remember what it was, and this is why I have the list of mathematical constants here. This is where I got all of these from. Oh yeah, there we go. It's the silver ratio. It has been discovered basically in the same frame of time like the golden ratio did, and the silver ratio is just another metallic ratio, just like the golden ratio. But it's a tiny little bit different, okay? You can read into it, but at least it's not annoying the fuck out of me. And the silver ratio means that some people realize that not everything is the golden ratio. Maybe something is in the silver ratio or the bronze ratio or maybe even the plastic ratio. Or, no, that's a different ratio. But since it's not as annoying, it's going to go into the suck of A department. Oh, next up, a number which sparked a bit of controversy quite a while back. And this number came even after the negative integers have been introduced. That is weird. Why? Right? And people got the natural numbers and the positive integers. No one got the idea that there could be nothing, number 0. And then they just said, okay, let's go into the negative. Let's make some dead, okay? And then only a few thousand years later, people said, okay, maybe there could be nothing. And that was number 0. Cool thing about the number 0 is that it's the so-called additive identity. Meaning if you add no more apples to your pile of garbage fucking apples, you're going to still have the same pile of garbage fucking apples. And the number 0 is so immensely useful in algebra, adding a meaningful 0 to an equation or in integration, just like the number 1. It's going to have a high spot. But it's going to be higher than the suck. I mean, the 1 only went into the suck category because of the construction of natural numbers with the Peano axioms. The number 0 is really important. Also, if you multiply something by 0, it's going to be deleted. That's the cool thing about 0. And also you can divide by 0, so this makes it even better. Sparking a bit of controversy in the mathematical community. Negative 1. Why is the number negative 1 important? Well, there are various reasons. It's the first number which is the predecessor of the natural numbers and 0, so it's the first negative number. But also, no number, no real number at least, squared, is going to give you negative 1. That's the imaginary unit. We are going to get into that later. But this is why the number negative 1 is so cool. It's the first negative number, and also no number multiplied by itself can give you negative 1. Which also sparked later the idea for the imaginary numbers as proposed earlier. So yeah, I think that's a really cool constant, and it's going to go into the C category because there's nothing more to it, honestly. Next up, we got psa. No, let us continue with the imaginary unit. Speaking of it, imaginary unit, without it we wouldn't be where we are at the moment. No quantum physics, no weird babbling about quantum tunneling and some non-zero probability of something going through your mama's arse. Yeah, it's pretty cool and used a lot. And without it, we couldn't live anymore, the mathematical community. And I think this really speaks for itself. And the best thing about complex numbers is that all the operations are still preserved. Associativity and the like, all of the crazy shit, what you can say about quaternions anymore, that's just not the case. So I think since it just sparked a whole new area of mathematics and functional and the like, and it's just one more reason to use the word anal in mathematics videos. I can give it an S set tier. It's just amazing. I like it. Next up, the constant that I can't remember what it was. Psa. It's the super golden ratio. I just put it in here because it sounded funny, but I have no idea what it is. The super golden ratio. In mathematics, two quantities are in the super golden ratio if the quotient of the larger number divided by the smaller number is equal to this one right here. Yeah, I mean, this makes total perfect sense. How could you not know that? How did I not know that immediately? And also it's the real root of x cubed is equal to x squared plus 1. That is cool. I should put this into a video. I think no one has talked yet about the super golden ratio. And because I didn't know about it and it sounds cool, it's going to get a C tier. Good one. You did well. Now next up comes mu. What about the mu? That's the connective constant for the hexagonal lattice. Square root of 2 plus square root of 2 as a root of the polynomial x to the 4th power minus 4x squared plus 2 is equal to 0. It just was a long name. I put it in here because probably only one person in the comments actually knows about it. It's going to get an XD tier, because it probably won't affect your life in any kind of way. Next up is this thing that I just copied out and I can't read it anymore because it's weird formatting. What is this? This is Wallis constant. It's the real root of x cubed minus 2x minus 5 is equal to 0. 1929. And this has been found in the year, where is it? 1616 to 1703. Wow. And it's just a constant of, oh yeah, I mean, it's rather groundbreaking. Because finding real roots of cubic polynomials was a huge task back in the days. I don't even think that there was a cubic formula out there at that point in time. Now I can see why it's so cool, and because it's so cool, it's going to go into the C tier. I can understand why that's cool. Next, the natural log of 2. Why is the natural log of 2 a cool thing? I can only guess it's in there because of the Dirichlet eta function, because it's Dirichlet eta of 1, which is one of the only few known closed form solutions of the Dirichlet eta function. Let's take a look at the list right here and let's see why it's so cool. Yeah, exactly. Because it has a very, very cool series representation from the Dirichlet eta function, and also it's the real root of e to the x is equal to 2. I mean, that is cool. But other than that, because I have found solutions so often to this one, and because I like it so much, it's going to go into the S set tier. I just love the natural log of 2. It's a cool thing. The only thing that I don't like about it is that it's written ln instead of log. Now next up we have this weird omega with the top. Do you know what this is? It's rarely used in mathematics, but this is the so-called var pi. There are variations of the regular Greek letters like var phi and the like, var theta. This is the thing that many people accuse me for. This is not a theta, what are you doing? This is the var theta, variable theta, and this right here is the variable pa. And this constant is known as the lemniscate constant. I have actually heard of this before. In mathematics, the lemniscate constant var pi is a transcendental mathematical constant that is the ratio of the perimeter of Bernoulli's lemniscate, or lemniscate, to its diameter, analogous to the definition of pi for the circle. Yeah, that's a very cool constant, and I think someone in the mathematics community on YouTube actually made a video on that already. And since it's nearly as important as par, it's going to go into the successor category. Okay, cool. Next up is this little symbol, gamma. What could this be? Oh, do you hear this? I think I'm getting hungry for some oily macaroni. If you're a regular viewer of this channel and back in the good old days where I did more abstract mathematics, I was doing a lot of oily macaroni here. And just because this constant is one of the coolest that I have ever known about, I'm going to give it an S here. It's just amazing. All right, next up what is that? That's capital omega, and this is what is also called the omega constant. And the omega constant is, if I'm not mistaken, the Lambert W function evaluated at 1 or E, I think. Let us take a look at the chart. It's the omega function evaluated, no, not the omega function, the lambda W function, Lambert W function, I'm being fucking retarded here, evaluated at 1. And that's a weird representation. You can only find it out obviously using numerical methods, and yeah, we have not made a separate video on that yet. But I have used the Lambert W function before, and just because I'm pretty neutral when it comes to it, we are going to give it a suck of 8 here. Next comes the E, and I think the E is the Erdős constant. Yeah, Erdős-Wolfen constant. And Erdős, a lot of regular number theory and also anal number theory. What is it? Let us take a look at that. The Erdős-Wolfen constant is the sum of the reciprocals of the Mersenne numbers. Yeah. Mersenne numbers, they are defined as being numbers of the form 2 to the n minus 1. Some of those can be prime. I think we only know about 30 or something. I think that's probably way too much. Mersenne primes, so Mersenne numbers which are also prime. And I think, yeah, this should be an irrational number if I'm not mistaken. If we take a look at the number field, yeah, the real numbers without Q, so the rational numbers, that means they are irrational, but I don't think that they are transcendental. I don't know. Do we know if this number is transcendental? He has shown that it's an irrational number, and despite its irrationality, the binary can be calculated. But I don't think that we know that it's transcendental. And because it has something to do with primes, somehow it's going to go into the C category. Now, next one, Riemann zeta function of 3, that's called the Apéry's constant. And I have made a video on that already in the anal number theory playlist. And since I love Riemann zeta and also Dirichlet here, it's going to get an 8 here. And I think Apéry's constant also had pretty meaningful meaning. It's the sum of the reciprocals of the positive cubes, it is defined as a number, blah blah blah. Yeah, but I think there was, yeah, we know that it's an irrational number. This is something that we have proven. And I think this is why it was so cool, because it's one of the only known values of the Riemann zeta function, where we know the irrationality, I think. Okay, next up. Another mu. No, we have talked about mu before, right? What was mu? I forgot. Yeah, that was the connective constant for the hexagonal lattice. No, we already used it. There's another mu in here. Oh no. This is the Ramanujan-Saltner constant. And I have heard things about it before. Yeah. This is the constant where if you take the logarithmic integral, that's the solution where the upper bound is going to be x and you're going to get 0 out on the other side. And yeah, that's a cool constant. This is basically the zero. I was describing it weirdly. That's the 0 of the integral, basically. Now my mother-in-law says that the cucumber salad that I crafted was delicious. So that's also cool. And because it has Ramanujan in its name and I'm annoyed by Indians, as you all know, it's going to go into the XD category. So G should be Catalan's constant, if I'm not mistaken. No. Here it's Gauss constant. What is meant by Gauss? No, where is it? Gauss constant. Once again, it's linked to the Lemnisek constant. 1 over AGM. I have no idea. Yeah, that is cool. Definitely an 80, I suppose. Okay, next up, capital A. Capital A, what is it? Yeah, it's the Gleichher-Kinkeling constant. It's one from analytic number theory once again. Let's just take a look at the thing here. And the Gleichher-Kinkeling constant is pretty fucking weird. Just take a look at that. This might ring a bell for you. E to the 1/12 minus the derivative of the Riemann zeta function evaluated at -1. That is curious, right? But that's the Gleichher-Kinkeling constant. How is it defined in Wikipedia? In mathematics, the Gleichher-Kinkeling constant or Gleichher's constant typically denote the capital A is a mathematical constant related to the K function and the Barnes G function. Exactly. I wanted to create a whole series about those functions, but I didn't have the time yet. But trust me on that, the theory is extremely cool and I really like it, and that's why it's going to go into the A tier category. Next up, the other capital G, which I thought is the Catalan's constant, and yeah, that's a really cool number. I have made videos on that already here on this channel. We got it several times. We already did a video on this integral representation, also on this infinite series and the like, and a few approximations and so on. And up until this day, we have no idea if it's irrational, let alone transcendental. But it's a cool number. We know quite a few decimal places, but nothing about the irrationality and the like. And since it's anal number theory, once again, it's going to make us gag. Gag, yeah. It's just what it says here in the tier list. Next we have x equals 2. This was supposed to be Dotti's constant. I have made a video on that. It's the basically solution to the equation cosine x being equal to x. It's a very cool equation. Watch the video somewhere in the analytic number theory playlist, but I really like it. It's a special kind of number that no one really cares about, because why should you? But it's a cool solution and I like it. And this one is going to go into the SZ here because I had a lot of fun researching this constant and the like back in the days. Now capital M, Mertens constant probably. Yeah, Meissel-Mertens constant. And this one is really important in anal number theory. Once again, I think I have a preference for anal number theory. And yeah, the Meissel-Mertens constant is the limit where n goes to infinity, meaning we sum up over all of the prime numbers, and the index right here is going to be 1 over p times the natural log of n. Analytic number theory, take the log of the log of the log of the log and you're going to get something out. And there's actually a closed form for that. Namely, we can rewrite this equivalently as the Euler-Maccheroni constant plus an infinite summation of the natural log of 1 minus 1 over the primes plus 1 over the primes, which is really cool. I like it. Researched it when I wrote my master's thesis and I really like it. Anal number theory, giving an A. Now e to the power. This is one that we actually know something about, if I'm not mistaken. This was the Gelfond's constant, I think. Let us take a look at that. And I think we know that it's irrational and also transcendental, following from Gelfond-Schneider. Gelfond's constant, and that's a transcendental number, one of the not many that we know about. And yeah, the proof is trivia and left as an exercise to the reader. And e to the power is actually the same as -1 to the negative r, which is really cool. And also r to the negative 2r. Yeah, and obviously you can sum this up using just a series representation. And it's a really cool constant. I really like it. I should make a separate video on that. But it's going to go into the suck of 8 here because we don't have many there yet. Next up we have 2 to the square root of 2. 2 to the square root of 2 is... I can't remember the name of the constant, but I think it's an irrational number. What was it called? Yeah, that's the Gelfond-Schneider constant. And by Gelfond-Schneider, that's a theorem, very cool one, telling you something about the transcendentality. About a number being transcendental. That's also a transcendental number. And I think this was the first one where they actually were able to use the Gelfond-Schneider theorem on it. Transcendental number, very cool, haven't used it. And just because we haven't filled the XD tier yet, it's going to go here. Next we got G, and no, this is not the gravitational acceleration. They say in this list that it's the golden angle. I have never heard of it before, but it's transcendental, obviously. No, it's not obvious that it's transcendental, obviously not, because what we are doing here is we are multiplying an irrational number by par. So it's not bound to be transcendental, but for some reason we have proven it to be transcendental, which makes it really cool. And in geometry, the golden angle is the smaller of the two angles created by sectioning the circumference of a circle according to the golden ratio. I should make a separate video on that, and just because it gave me a video idea, I'm going to go put it into the suck of 8 here. Now next up we got psi once again, and psi in this list is psi. Where's psi? Psi, where are you? Where are y'all? The reciprocal Fibonacci constant. I made a video on that already. It had a different name, but it's a cool constant. I think this was a PyMath episode, and it's most definitely an irrational number. And what this is basically is the infinite summation over the reciprocal of all the Fibonacci numbers. And it's a very cool structure. I really like it, and I think it had a different name. Or did it? No, this was the Fibonacci constant. I was being stupid here. Where's the Fibonacci constant? I didn't put it into this list, that's a bummer. But it's still a pretty cool number. And because it's cool, it's going to go into the C tier for cool. Next up we got delta. It's the Feigenbaum constant. It's the first one, I suppose. And it's a great number because it tells us something about chaos. And it arrived the first time to me, no, not in a Veritasium video, in nonlinear dynamics and also chaos. It's a very important constant, appearing in a set of differential equations. And because I love it so much, it's going to go into the... It's a delta, so it must go into the XD tier, right? Now next up, F. That's one that definitely goes into the SZ tier. That's the so-called Franzen-Robinson constant. I made a whole series on this one constant. And this right here is just the integral over the reciprocal of the gamma function. Might sound easy at first, but it was a horrible, very, very fun trip though. And you should watch the whole 3-part series on that constant. It's a fun ride, it's definitely worth it. And maybe there's also a link down there in the description. And last but not least, I don't need to elaborate here, and I thank you guys for watching. And if you enjoyed this tier list, you wanna make sure to subscribe to the channel. Also check out Flammy's Word, where I work my word all the goddamn time. And yeah, you can find the link to the tier list down there in the description and sort for yourself with your friends. Now until next video, you guys have a fun day. Ciao.